we're going to start talking about fields leading into Galois theory, which is like really kind of one of the coolest parts of the course. But I want to like do one more example here that I thought might be useful for you. So let's kind of finish off this business that we were talking about with three Nilpotent matrices. Are there? To somewhere. So here's my question. Let's say let me specify field. How many 3x3 matrices are there up to similarity? Nilpotent matrices. And how will we tackle such a thing? There's actually going to be one thing that's sort of useful. Does anybody know any theorems about nilpotent matrices and their eigenvalues? They must all be zero. So here's like a little fun fact. Yeah, and only if all so it's nilpotent if and only if all its eigenvalues are zero. How many of you have seen this before in your travels? Well, let's prove it. Let's try to get to the bottom of it. Let's suppose A is nilpotent. Somebody remind me what that means. Some power of A is zero. Well, actually, these are in by M matrices, so let me say A to M is some, you know. Now, what we want to do is show that all the eigenvalues are zero. So let's set up the eigenvalue equation. So lambda is an eigenvalue if and only if there's a non-zero vector v such that A equals lambda v, right? Okay. Now I'm going to do sloppy induction here. Apply A again here, right? But again, AB is lambda v. Everybody agree with that? And you all graduate students all quickly see the pattern. And so forth. So A K V lambda K V for all A in the natural numbers. Right. Well, so this means AM V is lambda M V, but AM is the zero matrix, right? So this is zero, right? But V is assumed to be a non-zero vector, so there's a power of lambda that is zero, right? But lambda comes from a field. So step one, we have shown that if A is nilpotent, then all its eigenvalues have any eigenvalue 0, right? How about the converse? Now suppose every eigenvalue of A is 0. And by every eigenvalue, I mean in some field extension, right? In the following sense, the characteristic polynomial of our matrix will be n by n. I'm assuming that all the eigenvalues are 0, right? I don't mean, oh, n is 10 and I only have 2 in the field or whatever, and they're both 0. I mean every eigenvalue, all in them are 0. I want to prove that A has to be a nilpotent matrix. Any ideas on how to do this? This is actually a nice application of all this canonical form business we've been working on. And in fact, I don't care what field you are, 0 is in there. Agreed? That means since all the eigenvalues are in there, I can actually bring this to Jordan canonical form, right? So the Jordan form of A, here we go. So the Jordan form of A it looks like something like this. It's got all zeros except maybe on the super diagonal, those stars mean either 0 or 1. Everybody agree with that? And just take a power of this and you will get 0. In fact, he might tell me what power for sure will work. The nth power. Because what happens, just do the computation yourself. When you square this, it moves the super diagonal elements up in the super, and then the next power is super, and it actually takes n steps. If these are all ones in the extreme case, it'll take n steps to march everything off. If these are all 0, it'll take the first power, but certainly that means the nth power works, right? So you can easily compute J to the n is 0. Well, this is P inverse ANP, but P inverse and P are both non-singular matrices. So this means that, and now multiply on this side by P inverse. So A is nilpotent. So let's go back to the original question. The original question being, up to similarity, how many 3 by 3 nilpotent matrices are there? And actually, I'm going to get a bonus out of this as well. All you got to do up to similarity is write the Jordan forms, right? So ask yourself this: how many Jordan forms do I get? Well, let me start with ooh, I bet that one's nilpotent. All right. Well, you could also have, so that's 3 Jordan blocks. I could also have a 2 and a 1. That's a 2 Jordan block and a 1 Jordan block. And I could also have a 3 Jordan block. And there you go. Notice the characteristic polynomial of all of these is x cubed. The minimal polynomial of this is x. The minimal polynomial of this is x squared, because you got to square this to get to 0. The minimal polynomial of this is x cubed. So actually, for the 3 by 3 case, just knowing the minimal polynomial is enough to tell you, right? For bigger cases, it becomes more and more difficult, right? So how about 5 by 5 nilpotent matrices? By the way, this also tells you something else as kind of a side bonus here. If you have a 3 by 3 nilpotent matrix, then the third power of it has to be the 0 matrix, right? There is no 3 by 3 matrix that is nilpotent that takes you 4 powers to get the 0 matrix. Yes.
Sorry, could you show again why those are the only 3?
Those are the only 3 Jordan forms, right? Because you've got 3 eigenvalues, 0, 0, 0, right? You got some choices here. You can either have 3 1 Jordan blocks here, or you can use those 3 eigenvalues to make a 2 Jordan block and a 1 Jordan block, or you could use it to make a single 3 Jordan block. And basically, it corresponds with the number of ways that you could take 3 and break it down as some smaller pieces.
And that middle one would be considered the same as if it was the 1 block.
Correct. Yeah, if you put the 1 block here, that's actually similar to this one, right? You can actually conjugate this one to make Jordan block down there, right? But in the abstract, I don't think it's obvious that deep in the depths of some Stephen King novel, you might find some 3 by 3 matrix that's nilpotent and takes you 4 powers. No. If it's nilpotent, it will get killed in 3 powers or less. So if you take any matrix and you take the 4th power of it and it's not 0, it's not nilpotent. Okay. Now, what about 5 by 5 matrices? Well, I feel like an idiot learning this in a graduate class, but I will do it anyway. Let's see if I can do it right. I think those are all the ways to write I as a sum of smaller integers. Anybody see if I missed one? Does that look right to y'all? I think I got them all there. So notice that if you have a 5 by 5 nilpotent matrix, its minimal polynomial will be, its characteristic polynomial will be x to the 5th power, period. Right? Let's go this way. One way to do this is a single Jordan 5 block. Minimal polynomial, x to the 5th. Correct. This one is a 4 block. And then, so you get this 4 block here. in 4 block, and then 1 block down here, minimal polynomial, x to the 4. Well, the next ones, we have a 3 and a 2, and I'll just write the blocks here. I won't fill in the whole matrix. And 0, 1, 0, 0. We also have 0, 1, 0, 0, 0, 1, 0, 0, 0. This is the 3 plus 2, and this is the 3 plus 1 plus 1. Both of these have minimal polynomial x cubed. And you see this effect starting to take place where the characteristic polynomial of both of these is x to the 5th, as are all the matrices, but the minimal polynomial isn't even enough information to determine it here, right? Because both of these have the same minimal polynomial, but they're not similar matrices, right? You have to have all the information with the invariant factors. Right? Let's do the rest of it. So we've got 2 more. 0, 1, 0, 0, 0, 1, 0, 0. This is the 2 plus 2 plus 1. And then you have 0, 1, 0, 0, 0. That's 2 plus 1 plus 1 plus 1. These both have minimal polynomial x squared. Notice again, the minimal polynomial is not enough to tell. And finally, you have just all ones, which is basically the 0 matrix. Notice for this one, if you know the minimal polynomial is x5, x4, or x, you know what it is. But if the minimal polynomial is x cubed or x squared, there's some ambiguity, and you have to know more about the invariant factors. Okay, any questions on that? Questions? Yes.
Is there like some formula that like generalizes for how many there are, or does it not follow that?
Yes, yes, and no. In the following sense, the number of ones that you get, if I follow your question right, the number of ones you get is basically you're looking at the partitions of an integer, right? So if I take 7, ask yourself how many ways can you partition 7? That is, how many ways can you write it as a sum of integers that are less than or equal to 7 or greater than or equal to 1, right? And that's difficult, right? It gets very complicated. Yeah, if I give you a specific integer, you could sit down and troll it out, but to give you something in general is difficult there. Okay, that's a good question. Others? Okay, so here we go into the exciting next chapter of our lives. Oh, also, we have another candidate in today that's giving a talk that I would like to go to. So if you're planning to see me between 11 and noon, just come talk to me today. Talk to me after class and we'll get some worked out. Okay. Definitely. A field is a unit of random identity such that 0 is a maximal ideal. Yeah, you probably very rarely see field defined this way, coming from the point of view of comedic range. But what this says is from an ideal theoretic point of view, feels very boring because 0 is maximal ideal. Notice that this means if our field is F, what this means is if you have a non-zero element, then The ideal generated by X is F, which happens if and only if X is a unit. So in other words, another way that's probably more familiar to you all is a field is a community ring with identity such that every non-zero element is a unit, right, or has an inverse. Another way that it's probably put to you. When's the first place you all ever saw the definition of field? My guess is probably linear algebra, maybe. Probably, when you were back in the day. And they go through this long list of, what do you do field? They go through distributed and all this business. Well, now, with a little more sophistication, it's sort of easy to wrap your head around because basically, so what's a field? Well, it's a mathematical object that is an abelian group under addition. And if you throw out the zero, it is an abelian group under multiplication. And you connect the addition and multiplication through the distributive law, and that's it. Okay. So let me sort of give you some kind of basic fields here. Make a following observation. No. Any field has a non-zero identity. So first question might be, oh, if you consider the zero ring, is that a field? I will not consider that a field for these purposes, right? So any field has an identity. Now, there's two important cases. There are two cases to consider. Number one, the identity is, of course, an element of this field. What is the order of the identity additively, right? Case one. This is called the case of characteristic zero. And what that means is if you start adding the identity to itself, it's never zero. 1 + 1 is 2, 2 + 1 is 3, and this process continues and you never get to zero. In this case, the field contains the integers in a natural sense. There is a 1-to-1 homomorphism from the integers into this field just by taking the integer n to the integer n times 1/f. The fact that n times 1/f equals 0 implies n equals 0 shows that this is a 1-to-1, a monomorphism of rings. So in this case, characteristic 0, the integers are contained in that, and therefore, if you take this a step forward,
Q is contained in it.
then Q is contained. An isomorphic copy of Q is contained in that, because since F is a field, you have to be able to invert any of these integers, right? So in characteristic 0, every field contains Q. This is called the prime subfield, right? It's up to isomorphism, it's unique, and it's contained in every field of characteristic 0. The other case, of course, is there exists n and n such that n one over there. This. And even though I mean it, it's notation, let me emphasize this. And in fact, in this case, you can say something about n. This would be prime time for me to quiz the class. What is special about n? It is prime. In this case, is prime. And I'm gonna do the old fashioned irreducible kind of thing. Notice if n equals AB with then the element but these two are not zero. And so what that means is if n is not prime, it has zero divisors, and fields cannot have zero divisors. In this case, n equals p prime and the field F contains. Okay, so here's the moral to this first part of the story. If you have characteristic zero, right? So in other words, if one has an additively infinite order and the field contains Q, if the characteristic is prime, it has to contain some P. Yes.
Is that supposed to be like case two, pick n, the minimal such n? That's fine.
Yeah, you're right. There exists an n. In this case, I should say right here, the minimal n. Good, that's right. Okay, other questions? Okay, so given a field, if you have a characteristic zero field, if you intersect all subfields of that field, you'll get the rational numbers. If you have a field and it's characteristic P and you intersect all the subfields, you will get CP. These are called prime subfields of the field. But now what we're going to do is look at, instead of fields inside, we're going to extend fields and make them bigger. In fact, we maybe gotten a little hint of that in many places in this course and others, but in particular in Jordan canonical form. Remember, you can't always bring a matrix to Jordan canonical form if your field doesn't contain all the eigenvalues, right? So maybe you're really angry at the world or whatever because you have a matrix, say, of the reals, and it's got eigenvalues I. Well, sometimes you can pass to a larger field where you get all the eigenvalues. In fact, you can always do that. So let me give you definition. But K be a field. F is an extension field. Okay. If F is field and K is contained in F. we say, by the way, let me point out something. Notice that F is in fact a vector space over K, right? Let's see, what do I call this thing? F is a vector space over K, right? Everybody agree with that? Because obviously elements of F act as vectors, and when you multiply a scalar times one of the vectors, it's still a vector space. So we denote the dimension of F over K as a vector space by that. And this is sometimes called the degree of the extension. And of course, this may be infinite. I'll give you an example in a moment. Also, if E is a field such that it's sandwiched in between K and F, including K and F itself, then E is intermediate field extension. Intermediate relative to the extension of F over K. And that'll usually, I hope, be clear from the context. So for example, these are all fields. Q, this is a small field containing Q and radical 2. Of course, everything in here is real. And everything here is complex. Are there bigger fields? Oh, you can go crazy. How about the set of rational functions? With complex, over the complex numbers. How about throw in as many indeterminates as you want? Right, you can go crazy, right, about making rational functions. So lots and lots of fields out there. And of course, everything in between are intermediate extensions. Now, let me kind of give you the first sort of counting theorem. Of course, this works for infinite. This is most useful, of course, when the extensions are finite, but this does work in general. Let yeah, so the opposite there. Suppose I have here. Anybody got a Christmas wish list on this one? So here's the big one. Here's the middle one. So we got the 3 bears here. This degree, F over K. What do you hope? You know what? I hope that too. that would be really groovy if that worked out, because the degree of the extension here, I would hope would be the product of these little jumps. Big jump is product of little jumps. And that's exactly the way it works out. As you might guess, this works best in we're going to use this a lot when the extensions are all finite. However, this works in general, and that's the way I'll prove it. So, to that end, let's let you prove this. Let you index set be the basis of F over E. Let's go E over K. And J, BJ be J. Okay, so we've got two bases here. Now what I want to do is I want to construct a basis. So my strategy here is I want to construct a basis for F over K and sort of count things. We show X is a basis for F over K. Okay. I didn't fill in that one yet. Anybody want to guess what our basis should be? Yeah, why don't we do that? I claim that if I look at all possible pairs, let's say I, J, and I cross J, then this will be a basis of F over K. So what I've done is I've listed my entire basis of E over K, my entire basis of F over E, and I just make all possible products, right? And I claim that this mess that I've made here, X, is actually a basis. The first thing I'm going to do is I'm going to show it spans. That one should be fairly easy. X spans F over K. Okay, so how are we going to show that? Well, what F be an F, right? I don't know much, but I know it's a linear combination over E of these VJs, right? Now, my index set may be really long, or really large, but give me this here. Then F is equal to, let's see, that's the basis of F over E, E1 V1 plus E2 V2 plus EL VL, where the VIs, VJs are in V and EI is in. Everybody agree with that? So yes, I know this index set may be big, but I re-index those VIs so that I don't have to write anything super complicated. Right, okay so far? Now where do I go from here? Right. Each one of those EIs and E can be expressed over K as a linear combination of the U's. And since there's only finite many of them, I can be sloppy about this. Well, so we'll say that EI equals 1 U1 or K each right. And right. But okay with that. So F is equal to, let me write some action form here. K I P so F is now equal to B1 E1 plus BL EL, which is E1 K I P B B1 plus sum L 1 K I P U P D L. So F is a linear combination over K of elements are formed UI. Everybody okay so far? Now, the next step we need is we need some linear independence here. So we now need linearly. We now need the set to be linearly independent. So claim 2. So as far as bases go, we show it spans. Now we need to show that it's linearly independent. So to this, suppose we have the sum over ij let's say this is K I J U I U J. By the way, this is a finite sum, of course. I only go over finitely many indices here. And let's suppose this is 0. Right? Because what we're trying to do is we're trying to show the set of elements, these elements in X are linearly independent. So we need to show that all those KI's are equal to 0. Well, so let's sum this. Sum over I. Let's look at it this way. This is R J, I. J. Now. Notice that these are elements of E. And these are distinct elements, these VJs are all distinct here. So since the VJs are linearly independent, the set V is linearly independent. So for all I, we have J UI is equal to 0. Right? Because every one of these pieces right here is in E. So this is the linear combination of VI's over E. And we know that this is a linearly independent set. So that means that each of these coefficients for every out I must be 0.
Do you mean for every G instead of because we're summing on A, so it should be like for each G, the things.
Oh, yeah, you're absolutely right. I didn't even see that, yeah. B is linearly independent, so for every J, this is 0. She's exactly right, because each of these coefficients must be 0. Therefore, for all I, for all J as well, Kij is equal to 0. So now for all J, this is 0. So for every fixed J, for all I, the Kij is 0. So X is linearly independent. Therefore, UI dj, ij, and I cross J is a basis. And notice that the size of my index set, which is the same thing as the dimension of this vector space, is the size of multiplied of each of these. Therefore, this thing is F over K, and this is whatever I was, is E over K, and J is F over E. And that's the point. Okay, any questions? Okay, so let me kind of give you well, I'll just introduce this terminology real quick. If F is a field and X and F is a subset, and I do mean set at this point, then the subfield of F generated by X is the intersection of all subfields that contain X. And the intersection K, since the K is an F and X contained out of O. Okay. So it's just the collection, the intersection of all fields that contain that set. This is also a field as well. And if say X is A1, A2, AN, so it's supposed to define F, then F of A1, A2, AN is the set of all P evaluated A1, AN, where P is a polynomial. So what this notation means is these are all polynomials with these things plugged in. This is actually the smallest ring that contains F and A. And its elements in that round bracket. This is set of Q, A1, AN, such that Q is a rational function. And that's N and F or where Q of A1, AN is defined. We're going to talk about how to build fields like this next time. Any questions? Any questions? We'll talk more about this notation. I'll give you some examples.